So let's think about using what we know from external flows to try to figure out some characteristics of internal flows. So for example, one thing we might want to know is about how long is this hydrodynamic entry length. So how long does it take the flow to become fully developed, at least from a velocity standpoint, right? So how long is this hydrodynamic entry length? So as long as the flow remains laminar, we can estimate that using concepts that we've already developed from external flow, right? So for external flow, we said that because this momentum boundary layer is basically being driven by a diffusive transport of momentum, it's obeying at least approximately this equation right here, where it grows like 2 times the square root of time, and this property that dictates how it grows is the molecular kinematic viscosity, right? So again, this is only for a laminar flow, right? But for a laminar flow, you would have 2 times the square root of nu, which is the molecular viscosity, kinematic viscosity times time, where time here is basically how long has it been in contact with the surface, so x over u sub m. So based on that then, if we want to know how long does it take, what is the amount of length required for it to become fully developed, we're basically asking, what is the position here at which the momentum boundary layer has grown sufficiently that it becomes bounded. So what is the position here at which point the momentum boundary layer reaches half of the hydraulic diameter, right? It extends halfway across the duct. So if I plug in dH over 2 here for this momentum boundary layer thickness, and I plug in x sub FDH laminar, so x fully developed, hydrodynamic, laminar, right? So this is my laminar hydrodynamic entry length. That's what this is right here. I have an equation that lets me relate, or at least calculate, x sub FDH laminar. So let's just do a little bit of algebra. So we'll square both sides. So here we have dH squared over 4. Over here I have 4. And then I've substituted in the definition of kinematic viscosity, mu over rho. And here's my entry length over u sub m. Typically this is given to you in terms of diameters, right? So it's the entry length normalized by the diameter. So I just bring one of these diameters over here, and then everything else I put on the other side. So here's a 1/16. Let's see, a rho u sub m. I'm left with a diameter here divided by a mu. And then if I look at that, I realize that's exactly the Reynolds number we just decided was the right Reynolds number for internal flow. So the laminar entry length divided by the diameter is about 1/16 the Reynolds number, right? So 0.063 times the Reynolds number. And this is the equation you would find in most books if you went and just looked up, okay, how do I calculate the laminar entry length? But you can see where it comes from, right? It's basically just saying, I know how laminar boundary layers grow. How long does it take for it to grow to be 1/2 of the hydraulic diameter? All right, so that's not surprising, I guess, when you think about it, that this would be the equation. The other thing we can understand from things we already know is when will an internal flow be laminar versus when will it be turbulent, right? So we just said that we have this situation where if the boundary layers remain laminar, I know how long it will take the boundary layers to come together and hit this fully developed region, right? So that's what this equation is here. This is saying as long as the boundary layers remain laminar, then I can calculate this laminar entry length. And then if we go back and think about what we learned for external flow when we were talking about turbulent concepts, we said, there is a critical Reynolds number, and we can define it either based on the boundary layer thickness or here based on the position. But there's a critical Reynolds number at which point the flow is likely to transition from laminar to turbulent, provided that it can grow, the boundary layer can continue to grow without bound, right? So, this critical Reynolds number defined based on x was something like 5 times 10 to the 5th. but I can use this equation to calculate the position on the surface at which point I'm likely to experience a transition from laminar to turbulent flow. So let's look at these two pictures side by side, right? If I go over here to the left and I think about this picture, if I have a situation where these boundary layers come together and they're laminar and they finally become a fully developed flow, moving downstream to the right, if I'm laminar all the way to this point right here, I'm never going to transition to turbulence, right? Because nothing changes anymore. So if this happens, right, if this entry length, this laminar entry length is smaller than the length required for the external flow to become turbulent, then I would expect that I would always stay laminar. On the other hand, if this length here, this critical length required for it to become turbulent, is smaller than this entry length, well, if it transitions to turbulence, then it's going to stay turbulent forever, right? So basically, it's a competition between these two lengths, right? Does the flow transition to turbulence before or after it would become fully developed as a laminar flow, right? So if this laminar entry length is less than the critical length required to become turbulent for an external flow, then you would expect the flow to be laminar. If this equal sign changed, if this were greater, it would be turbulent, right? So that transition point is when these two things are exactly the same. So hopefully that makes sense if you think about it a little bit. But that will let us basically figure out the criteria that will delineate a laminar and a turbulent external flow. When is the laminar entry length equal to this critical length required to become turbulent? So we're just going to take, here, let's just go back. We're just going to take this equation here, and we're going to set it equal to this equation here. And that's going to be, our criteria for whether we have laminar or turbulent flow. So that's what I've done here. And you do just a little bit of algebra. So this is my laminar entry length. This is my critical length required for turbulence. What did I do? I just brought over the rho and the u infinity and the mu to this side, so rho infinity mu, and of course I had a dh, I kept that here. And then I brought the 0.063 over here, and so I have the critical Reynolds number, which is like 5 times 10 to the 5th divided by 0.063. So over here I have the Reynolds number, and then this other group is the Reynolds number again, so I have the Reynolds number squared is 5 times 10 to the 5th divided by 0.063, and if I take the square root of both sides, I get that the Reynolds number for an internal flow that delineates whether I'm laminar or turbulent is about 2,800, right? Depending on what book you look in, it might be 2,300 or 3,100, but it's right in that range. It's not a hard and fast rule, just like for an external flow. It's not exactly 5 times 10 to the 5th, right? You get different behavior depending on a whole bunch of other characteristics, but that's maybe right in the center of the range where you would expect this to happen. So this is a pretty good criteria, right? If you calculate your Reynolds number for an internal flow and you find it's a lot less than 2,800, you probably have a laminar flow. If it's a lot more than 2,800, you probably have a turbulent flow. When you're designing a device, you actually typically don't want to be anywhere near this transition, because what happens then is you don't really know what you have. You have two different kinds of behaviors, and there's a pretty good likelihood of either one happening, right? So most designs stay away from this region altogether if they can. Yeah, so the other thing, just to sort of go back and remember, we did also say that you could define a Reynolds number based on the momentum boundary layer thickness, right? This is way back when we were talking about turbulent concepts, and we said if you define a Reynolds number based on momentum boundary layer thickness, that's a much more physically realistic Reynolds number. It really actually then represents the ratio of inertia to viscous forces, and so if you think about when that transition is going to occur based on the size of that Reynolds number, it's about 3,500, and not coincidentally, that 3,500 is not that different than when you would get a transition to turbulence for an internal flow. It's actually a little bit smaller for an internal flow typically, and that's probably because the core of the fluid near the center is actually speeding up, right? So you have that additional Reynolds or inertial force. So I guess one last sort of picture that hopefully helps with this is if you have a situation where the Reynolds number is substantially higher than 2800, you would expect then that you transition to turbulence, right? And it's a turbulent flow. So what would that really look like? So if you look at the developing region of the flow, you would still expect that initially you have a laminar boundary layer that grows, right? Because it takes some time before you transition to turbulence, right? So you get this laminar boundary layer. But at some point, before the laminar boundary layers come together, you transition to turbulence, right? You hit that critical position, that critical Reynolds number that causes you to transition to turbulence. And that happens, again, before you would come together as a laminar flow. Once that happens, I would expect a few things to happen, right? The first thing is that the turbulent boundary layer grows very, very quickly, right? And the reason is because the turbulent viscosity, as we talked about, is so much higher than the molecular viscosity. So that turbulent boundary layer is going to grow very quickly. And what does that mean for an internal flow? That means it's going to become fully developed very quickly after it transitions to turbulent, right? So whereas a laminar boundary layer might have a relatively long entry length, a turbulent boundary layer is probably going to have a relatively short entry length, and that's because once it transitions to turbulence, that development happens very quickly, and the turbulent boundary layers come together, and you have a fully developed turbulent flow. One way that you'll see that is when we look at correlations in a lecture or two. You'll notice that many of the laminar correlations will have methods for putting in the length and actually correcting for the entry length region, whereas many of the turbulent correlations just ignore that entry length region as being unimportant. And that happens because in a turbulent flow, the development happens very, very quickly, right? Once the turbulent flow happens, right, you would expect the velocity distribution to change quite a lot. So here's a developing laminar flow, right? We have this nice gradual velocity gradient that goes from the core to the wall, right? When I transition to a turbulent flow, I expect to get back to that situation where I have a viscous sublayer very close to the wall, and that's where most of the velocity gradient happens. And then the core is actually a relatively uniform turbulent core, right? The velocity in here, at least the average velocity, is fairly uniform. In terms of shear stress, what do you expect to happen? So here we have laminar boundary layer that's growing. I know that here where it starts to grow, I get a very high velocity gradient, right? A very thin boundary layer, so it's going to be a high shear stress. But as it grows, that shear stress is going to drop. And then here it transitions to turbulence. And once I get to the turbulent flow, what's going to happen here? Well, I'm getting a very high velocity gradient again across that viscous sublayer. So the shear stress is going to skyrocket upwards, right? And then for this little bit of region where I'm still developing, the viscous sublayer grows a little bit, so the shear stress actually drops a little bit. But then once I hit fully developed, again, nothing changes. Whether it's laminar or turbulent, nothing here is changing, and so my shear stress is constant, right? So you can sort of use this mental image of what's going on to really understand physically what you would expect for your engineering quantities like shear stress. And what we'll show next is that shear stress really tells you about the pressure drop, which is what you probably care about a lot. So let's go on to the pressure drop then, right? We talked a lot about shear stress. We talked a lot about velocity distributions, and those are things that I think it's sort of where you start, because those are the things that you can understand based on conceptually what the flow is doing. But in the end, if I have flow through a pipe, what I probably care about is the pressure gradient and the pressure drop. And the reason is because if I have flow through a pipe, as an engineer, I got to come up with a pump or a blower or some kind of fan or something that actually pushes the flow through the pipe, right? And so, if I'm sizing a pump, they're not going to size it for me based on shear stress or momentum. They're going to size it for me based on flow and pressure drop, right? So we have to take these quantities, like the flow and the shear stress, and we have to turn them into engineering quantities of interest, which is the pressure drop. So the way that we do that for an internal flow is with an x momentum balance, right? And we've talked about x momentum balances, quite a bit actually. We talked about them when we were deriving the x momentum equation. We're going to start from the same place. We're going to use just kind of a slightly different control volume. So here's our x momentum balance. What we said is that x momentum is not a conserved quantity, right? I have the rate of x momentum in has to equal the rate of x momentum out plus the rate at which x momentum is stored in any control volume, but I do have this additional term over here, which is the sum of the forces in the x direction will augment the rate of x momentum in, right? So here's my x momentum equation, and we're going to apply this to a differential control volume on the flow. And this differential control volume is not going to be differential in both x and y the way it was when we were trying to derive a governing partial differential equation. This differential control volume is going to be differentially small in the x direction, but it will extend all the way across the surface, the cross section of the duct, right? So it's encompassing this entire cross section that flow can travel through. And then we're just going to go through and think about each of these terms one by one.